तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Yeah, last class we were looking at the constitutive equations, and we're going to continue that. Maybe we'll finish it, summarize the whole thing and finish this topic. The topic is very, very vast. In fact, there can be a complete subject on constitutive equations and the relationship between so many different quantities which we have mentioned in the past about 4 or 5 classes. We are not going into the details, basically because we have to understand all the terms that are defined. So tomorrow if you want to look at any other new material or any other constitutive equations, what you have to know is only the terms. And we are also, I hope you understand the big picture of where we are coming from and then fit in the smaller pictures accordingly. In other words, if you remember, we came from the isotropic or anisotropic and isotropic materials. We then branched off at the isotropic material. Then we said that for isotropic materials, then we have a special rule. Okay, we said representation theorem. And then from there, we developed a very, very general relationship between the stress and deformation. If you remember, this was the result of my representation theorem. It stated that for a scalar value tensor functions, if isotropy is going to be satisfied, then it would be possible for us to write this in terms of the invariance. Okay, from there we wrote a very general equation. So that equation is valid for all isotropic materials. Okay, from here we are going to again branch off. Now before we branch off, we ultimately, when we left in the last class, we said that the stresses, different measures of stresses, for example, second PLO Kirchhoff stress, the first PLO Kirchhoff stress, the Cauchy stress, and so on, can also be written in terms of stretch. Okay, which means that, note this carefully, that stretch are nothing but the eigenvalues, okay, of the square of them are the eigenvalues of C and so on. So, or in other words, U and so on. Or in other words, when I write these stress measures in terms of stretches, automatically the stress measures do have only the diagonal terms. Okay, that's why we had written it like this. Okay, diagonal terms. It is very common today to work, most of the numerical analysts work with stretch-based constitutive equations. That's the reason why I had put this down. Okay, it becomes much simpler to implement it using finite element analysis, in finite element analysis, instead of looking at the constitutive equation as we did before this in terms of just I1, I2 and I3. Okay, not that that's not correct. I mean, it's not that it's wrong, but it's easier to work when we look at this kind of things. We'll come back to this in a minute. But before we do that, let us now see where in this picture we are. So we have just finished isotropic materials. So these isotropic materials can further be classified into 2 categories. What are they? We call them as incompressible isotropic materials as well as compressible isotropic materials. Same way the other branch also goes off, anisotropic materials and so on. Now, what is the difference? Let me just point out the difference. Whether you understood that. The difference is that the representation theorem is no more valid. In other words, we can't represent this psi which I had done before in terms of I1, I2 and I3. In fact, interestingly, what we need is, for an anisotropic material, what we need is more number of this kind of invariants. And these invariants are sometimes called as, say, I4, I5 and so on. So there are more number of invariants, okay, to take care of, say, for example, fiber orientation, how the fiber is oriented. Okay, that becomes important when material becomes anisotropic, for example, in a composite material, or for example, if you take heart muscle, where the collagen fibers, okay, run at a particular angle. These becomes important. So in which case, what is that we do? We take a very similar expression, but the only thing is that we now have more than 3 invariants. Okay, some of the purists still question whether this I4, I5 and so on, what does it mean? Do I put this down? Are we correct? But people use it. I think it is mathematically quite sound. So people do use this, putting down, okay, a number of other invariants when anisotropy is encountered. It's a fairly new topic. Not much work has been done till very recently. In the 90s, people have started working on this kind of anisotropic strain energy function with I4, I5 and so on. Though in the 70s and 80s have a few papers, but basically people have right now started putting this kind of thing. This I5 may keep increasing depending upon the anisotropy and so on. But I'm not going to deal with this. I'm not going to write down what is I4, what is I5 and so on. Suffice it to say that these are introduced and these depend upon, say, for example, fiber orientation. Okay. Now let us now look at the incompressible and compressible isotropic materials. Okay, what are they? Now what is incompressible material? Incompressible materials are ones where J is equal to 1. Let's remove compressibility for a minute. Okay, I'm going to just tell you the path which is followed here. It's just that incompressibility means that J is equal to 1. And what does it mean for us? It means that I have to satisfy this constraint. So these materials are also called as constrained materials. Constrained materials. Constraints are very important. It has again there's a lot of theory, a lot of mathematics associated with it in pure continuum mechanics. But for our study, it is sufficient to say that the strain energy function now has one more term added to it. In other words, it's not only a function of this gradient, deformation gradient, but also is a function of what is called as minus p into j minus 1, where p is the Lagrangian multiplier and is identified to be the pressure term p. Okay, it's a very common thing that you do usually when there is a constraint. Okay, you put, when there is a constraint condition called j is equal to 1, what you do is you have this j minus 1 multiplied by the Lagrangian parameter or Lagrangian multiplier, and then determine the Lagrangian multiplier as well. Okay, so in other words, what it really means is that this p, which is a scalar quantity, okay, though identified with respect to pressure, is one which can be determined only by means of kinematic conditions, or in other words, boundary conditions. In other words, this is not supposed to do any work. It's non-working scalar quantity, which actually comes because of the condition that j should be equal to 1, and that this has to be determined. We'll do a small problem later, and has to be determined only by a scalar quantity. In other words, what does this give us? This gives us, going back to my first Piola-Kirchhoff stress equation or the relationship, remember that we wrote this like this. Do you remember that? So instead of that, we have to now write down this as this strain energy function, the derivative of this strain energy function which is put forward here, and so that becomes minus P dou J by dou F. Remember that yesterday we derived this. So what is that? Look at what we did yesterday. Dou J, what is J? Determinant of F. Dou of determinant of F by dou F. We did that yesterday. Yeah. Yes. What did we get? Good way to look at what you did in the last class. Determinant of F into F inverse transpose. So what happens here? So determinant of F should be equal to 1. So minus P F inverse transpose plus note that we have just deviated a bit from our original expression in the sense that there's an addition term here. And please also note that there's some questions. Please also note that dou of J by dou F, okay, J is a scalar quantity. Dou of J of dou F, where F is a second order tensor, results in a second order tensor. Okay, it's very important. So when I differentiate a second order tensor with a second order tensor, the result will be a fourth order tensor and so on. Okay, so obviously because dou J by dou F 1 1 you can write, 2 2 you can write, and so on. So you get F inverse transpose. Let me see. Can you write down what is there for S? What would be the expression for S? Because I understand that there are a lot of equations and examples. It's a nice thing to do, to look back and see what is the relationship between S and P and see whether you can determine that. Yeah? S is equal to minus P F inverse transpose. That's the relationship. In this case it becomes S is equal to F inverse P. Okay, so plus F inverse dou psi of F by dou F. Go back and refer to a relationship between P and S. Okay, in this case it becomes S is equal to F inverse P. Then that's the second one. It's a very important relationship. So these are again general relationships for incompressible material. General relationship for incompressible material. When you want to define this for isotropic incompressible material, we again go down, okay, and then express this. Very simple. Express this quantity like what we did before. See in that whole map where we are. That will give you an excellent picture. We are not deviating from what we did. In other words, this is another special case. When I say isotropic, then immediately my attack is on this. Okay? In other words, this can be expressed now in terms of the invariance, or we can also express it in terms of the lambdas. Right? Can someone tell me what should be the relationship, or what should be sigma? Let's see. So what should be the relationship? You know the relationship between them. Minus, of course, minus P is going to be there. Minus P. What is the relationship between sigma and S? Go back and refer to it. Yes, J inverse becomes 1. So so sigma is equal to J goes out because it's equal to 1. F into F, S F transpose. J inverse J is equal to 1 in this case. So apply that there. So you will get sigma is equal to minus pi, right, first, plus right. Now we know that this commutes, so you can write this as F dou psi by dou F transpose. Right. Now just to understand what we have done, I want you to, is this clear? Any questions?
So here should be determinant of F inverse transpose.
P into F inverse transpose, yeah.
Because dou of determinant of A by dou A was determinant of A into A inverse transpose.
Yeah, A inverse transpose becomes F inverse transpose. So that's exactly what we did here.
That is both were under determinant.
No. Determinant of, what it means is determinant of A, okay, dou J by, that is dou J by dou F is equal to determinant of J into, that's determinant of J into F inverse transpose. The determinant of J became 1. So that's the doubt. Okay, why I left out J is because J became 1, because that is the incompressibility condition. That is why J is not here. Okay, so that's why I write straight away minus P F inverse transpose. Okay, so determinant of J into F inverse transpose, determinant of J became 1, and that's it. So, okay, suppose now I reduce this to isotropic. I have not yet reduced it, now I am going to reduce this. If I reduce now this to the isotropic case, so in other words, isotropic incompressible elasticity. How do I now write this down? Let's see, go back to what we did in yesterday's class, and let us see, you write down the general equations quickly. How we write, you take this, okay, and then write down for isotropic case. In other words, what isotropic case means, as I told you, this can be expressed in terms of, I1, I2, and I3. So go back, look at your expressions in yesterday's class, and then now write down what should be the expression for, say, S and sigma. So let's, of course you can write it down for P also. Let's say that you just write it down for S. Let's see how you write it down. Go back to yesterday's class and look at that expression there. So what are the expressions you had? 2 into dou I1, yes, into I minus into C, yes. So where does it now stand? So what is the term that is not going to be there? So there are terms involving I1, differential of I1, I2, and I3. No, so what is that you are going to get? Simple. Well, it's simple that the I3 is not there. I3 is equal to 1. So you will not have that term. So you can write that down to be minus P. Okay, that is, what is F inverse? F in J is equal to 1. That's all. Okay, so F inverse transpose can be written as C inverse. Okay, that's equal to minus P C inverse plus all the terms that go with it. That is 2 into, read out, 2 into I1 plus I1 I minus into C. That the third term won't be there. So that is it for, that's the general, look how we have very neatly reduced. Now this is the isotropic incompressible elasticity. So what will happen to now sigma? Sigma, I mean, from, you can write it in terms of B or B inverse. I'm just not going to write that. You can do it, okay? So you can write that also in terms of sigma and P. So that's the one aspect of it. Now, as I told you right in the beginning of the class, that it is possible to express this whole relationship in terms of the eigenvalues as well, lambda 1, lambda 2, and lambda 3. So in which case, the relationships just reduce to this. How does it? Let's see what you do. So sigma A, I have written it here, it is here. So what would be the, so J inverse will go off here. So sigma A, we've seen what it is equal to minus P plus lambda A and so on. But there's a small change for PA. Okay, I'm not, as I told you, I'm not going to derive this. PA will have, okay, and in fact, yes, will have, see, note that, note this, sigma I had a minus Pi here, right? And yes, I had a minus P C inverse here. So that C inverse term, okay, I didn't derive P, let's not worry about P now. Very simple, you can convert it. So what will be the SA term now? First term, say when we had minus Pi, we had minus P. So minus P C inverse. So lambda A squared is the eigenvalue for that. So this will become minus P by lambda A squared. So look at this term here, minus P, the C inverse term, first term, if I want to write it in terms of the stretch, becomes minus P into lambda A squared, right? Plus 1 by lambda A, that's the first thing. I mean, that's the thing which we had previously. I have not derived this completely. I mean, derivation is quite involved, but the second part I didn't derive it, just wrote it down. Okay, we can do that. So standard derivation. People who are interested can look at nonlinear elasticity, nonlinear solid mechanics by Holzapfel, or the book by Wood. Okay, the derivation is there. There's time, if I have enough time today, maybe we will just indicate how to do it. Okay, so that completes our picture on incompressible elasticity. So what does it mean? It just simply means that that's the crux of the whole story. Okay, so given, these are general expressions. So given a function here, this function here, okay, I will be able to get these things. Of course, for an incremental formulation which we are going to follow, I'm jumping 2 steps, which we are going to follow, we need something else as well. We need the relationship between delta S and delta E. In other words, dou S by dou E is what is also required. Okay, these formulations are slightly different. Okay, I will indicate to you some of the final forms, maybe the next class when we enter again into finite element analysis. Okay, but what I want you to follow is the theory as to how this overall picture emerges. So we now move into compressible elasticity. Again, a general compressible elasticity followed by isotropic compressible elasticity. right? One of the things that is done in compressible elasticity is to define F in such a fashion, or split F such a fashion that we have a volumetric part and an isochoric part, right? In other words, a deviatoric part and dilatational part. Before I forget, one of the things which I want you to remember is that though we have clearly demarcated saying that materials are either incompressible or compressible, okay, we demarcated the material into two, many of the rubber materials that are used are actually nearly incompressible. But most often in numerical analysis, this is treated as an incompressible material itself. Okay, many people treat it as an incompressible material itself. Okay, though we say that they are nearly incompressible, or in other words, nu in a linear scale, in a linear case, is nu is equal to 0.499 or 95 to 99, not equal to 0.5. When once it is nu is equal to 0.5, we say that the material is completely incompressible. But many formulations and many examples, if you see, people continue to work with the incompressible part and say that it is incompressible as well. So for a compressible material, F is decomposed into a volumetric part and a deviatoric part. And in fact, F is written as J power, I think we did that before, anyway, I'm just writing this down, J power 1 by 3 I F bar. So that you can see that the determinant of F bar is equal to 1, and same way you can write C is equal to J power 2 by 3 I C bar. Note that both of them, of course, are second order tensors. This is due to very early work by a very famous chemist, in fact, Flurry. So this is called as Flurry decomposition. It's called as a Flurry decomposition. So what we now do is that, so there is a deviatoric dilatational part. What we now do is to say that there are two versions of psi, the strain energy function. There are two things. One is due to dilatational part, volumetric part. The other is isochoric part. There's no volume change, or deviatoric part. So we put down two psis. Before that, let's write down some expressions which we may need later. Dou J by dou C rather is equal to, we know that J by 2 C inverse. So some of the expressions, and dou of J power minus 2 by 3 by dou C is equal to minus 1 by 3 J power minus 2 by 3 C inverse. And then a few more which we may need. Okay, in fact, you may need them for doing problems. Suppose I have dou of phi A, okay, that is a scalar quantity and a vector quantity of dou C. How do we write down this differential? Dou of phi A, scalar and a vector quantity, okay, is written as A dyadic, note this, A dyadic dou phi by dou C plus phi dou A by dou C. Of course, these are second order tensors. So what is the result? Look at this. Dou of phi A by dou C. So what is the result of this? Second order tensor. Second order tensor. So this is a fourth order tensor, and that's the relationship. No, any second order tensor. Okay, this relationship may be important to you. Now I need one more quantity. You'll see why I need this. I want dou C bar by dou C. Dou C bar by dou C. So how do I get that? Dou of, from here, C bar is equal to J, that's equal to dou of dou C, J power minus 2 by 3 here, okay, C, I, C, or in this case you can remove that and put straight away I into C is C, so you can put that as well. So compare this with what you did before, or what I wrote down before, and let's see what this gives rise to. So the first term is phi dyadic, dou A by dou C we had. So phi dyadic, here phi is J power minus 2 by 3. So this is equal to J power minus 2 by 3 to dou C by dou C. What is dou C by dou C? But I, fourth order I, beautiful answer. So that's a, so it's a fourth order I. Fourth order I is written like this. So fourth order I is written as actually delta Ik delta JL, because there has to be IKJL, delta Ik delta JL, and what are the bases for this? EI, EJ, EK, sorry, EL. So that's the fourth order I, fourth order unit tensor. So that's the first part of it. So what is the second part? Refer to what I did and tell me what is the second part. C, dyadic of dou J power minus 2 by 3 by dou C. So substitute this dou J power minus 2 by 3 dou C from what I had written down there, minus 1 by 3 J power minus 2 by 3 C inverse. Substitute that into this expression. Okay, substitute that in that expression, and ultimately, I'm just going to remove all this. You can write down dou C bar by dou C to be J power, you can take that out, minus 2 by 3 fourth order I minus 1 by 3 C dyadic C inverse, where people identify this as a transpose of what is called as a projection tensor. We have already seen what a projection tensor is. It's a fourth order projection tensor. It doesn't matter, okay, just it's identified. Let's not go into the theory of projection tensors, but this is what it is. We will see in a minute why we need all these kind of things. Again, all of them are algebra, so that's why I'm not very perturbed by it. But the theory comes from here. That, in fact, if you really look at it, the whole theory can be very easily understood, not more than one class. The rest of it is only algebra. Okay, there's nothing more than that. So now the theory is very simple. What we are going to do is the total strain energy function is split into two parts. That's all is the theory. One is the volumetric part plus the other is the isochoric part. The next two sentences are theory. Then again we will come to algebraic manipulation. So in fact I want you to summarize all the theory. Okay, algebra is always there. The tensor algebra is, I mean, maybe it may put you off, there's so many equations, but I would like you to understand the theory behind it. Once I write like this, again see that we are going to use the old theory, what we know. What is that I'm going to do now? Let's see someone. So ultimately I want to develop a stress strain relationship or stress deformation relationship. So what do? All of them are inelastic material. So my choice is very simple. I find out psi dot. Okay, so where volumetric part J dot plus the isochoric part, which is written in terms of C bar. Now that's what is, this can be written in terms of C, or previously now it's written in terms of C bar, so that this can be written as C bar dot. Is that clear? Yeah.
Why are you using C bar here? And C
Yeah, because please note I had split C into two parts. One is C and C bar. The C bar, what is C bar? I have removed from C bar the volume changing part, because we are talking about compressible materials. So I have removed that part, and C bar now represents the isochoric part. C bar represents the isochoric part. So when I want to look at the strain energy function, then I have to write this in terms of the isochoric part or C bar. I can't write this obviously in terms of C, because C has that compressible part, and that compressible part has been removed and is put here. That's all. So what do? Next step. Having done this, what is that I do? It's very simple. There's nothing great. Exactly what we did in the previous class. Let's see. How did we get the? Can anyone answer? Why did I go to psi dot previous class? Previous couple of classes back. Because I wanted to substitute this into my, no, where is that I want to substitute this? CDI. Okay, Clausius-Duhem inequality. Only thing is that I am removing that inequality part because I am still in elasticity. Right? So remember that we had an equation of the form F dot minus psi dot equal to 0. Okay, so that's where we are still there, nowhere else. So what we are trying to do now is S colon. Okay, now P, I already told you that we are going to work most of the time with S. Okay, because S is, though S lacks physical meaning, I'm very comfortable with S because it is a symmetric tensor. So we can write that in terms of S and C dot. So C dot by 2, okay, minus a number of terms, and I'm not going to write that down there. Probably you can write it down, okay, because you know many of them. What is J dot? What is all these things in terms of C? So we can. Yeah, this is a small change that we should do. I think 1 minute. Yeah, there's a small change. Just look at this. So those, because if I want to substitute it back into this expression here, okay. So this is written in terms of C bar, no doubt. Okay. This is written in terms of C bar. But when I want to substitute this, it has to be in terms of C because this is C dot. So colon or into, in fact, I have to write this down as dou psi iso C bar by dou C bar into dou C bar into dou C. Okay, this should be colon C dot. Right? I mean, because I have to substitute it back into that expression. So that ultimately, this expression, what I have written here, when I substitute it back here, this can be written now as S minus J, you know that before, dou psi volumetric, I think I wrote that as volumetric, yeah, dou psi volumetric by dou J C inverse minus J power minus 2 by 3, that is dou C by dou C bar is what I'm writing. Okay, that we derive that's here into all these things. Now it becomes transpose of it when I convert this double dot into in the matrix notation, it becomes transpose. So ultimately you can write that, okay, as actually P colon 2 times dou iso by dou C colon C dot divided by 2 is equal to 0. So remember this is very similar to or exactly the same as what we did. Only thing is you have to be careful with all the terms, whether you have included all the terms. Again, that is algebra. Okay, and just see that all the terms are there. In other words, what this is what we call, you remember, Coleman-Knoll procedure. In other words, what it means is that S is equal to this plus this. Okay, so S consists of 2 parts now. So in other words, yes, just check up whether I have included all the terms, or else you can just check that. Okay, or else you can replace P by this whole thing. You can write that down. So in other words, S has 2 parts, S volumetric plus S isochoric. So the first part is the volumetric part, the second part is the isochoric part. So that's the volumetric part. That is the isochoric part. So the major thing in compressible elasticity is to split psi into 2 parts, volumetric and isochoric. Yeah, you can keep substituting, now do a lot of algebra, okay, to express all these things in terms of various quantities. I'm not going to do that. I'll leave it at this, okay, that this is the concept that we usually follow. Further than this, I think you can see many of the standard textbooks on continuum mechanics, or you can, in most papers themselves, derive many of these relationships. Will not continue further, okay, than this. Right? So that is compressible elasticity. Now, of course, I can again say compressible isotropic elasticity, in which case I can express that iso in terms of I1 bar, I2 bar. I can keep on extending this. The concept is the same. Is this clear? So let me summarize this so that you are not lost in the whole thing. What we did, the first thing what we did was to write down Clausius-Duhem inequality. Remember that we did first Clausius-Duhem inequality. We finished that and then came to the constitutive equation. In constitutive equation, we defined an elastic material as one where there is no dissipation. Right? So that right-hand side inequality sign becomes equality sign. Right? So we wrote down the expression for P to be just dou psi by dou F. That's concept number 2. Concept number 3, what did we say? We said that materials can be isotropic or anisotropic. We went to isotropic. We said that it can be, or the psi can be written in terms of I1, I2 and I3. Concept number 3. Okay. Then 4, we expressed in a more general form S, P and sigma. The next concept is that we said it can also be expressed in terms of stretch, and we expressed sigma S and so on in terms of stretch. Okay. Then this is for general isotropic hyperelasticity. Then actually we realized that isotropic hyperelasticity can be now classified into incompressible and compressible hyperelastic. So we have to now reduce that general thing to these two conditions. So when we came to isotropic hyperelasticity, we realized that we have to put that J as a constraint, put J is equal to 1. So what we did was to add to that strain energy function a constraint condition, okay, through a Lagrangian multiplier, P is into J minus 1. Right? We did that. And then the rest of it followed in a very similar fashion as we did in the first case. Then when we came to compressible elasticity, what we have to do is to now distinguish between or split this into volumetric part and the isochoric part. Okay? So then we again developed equations S using Clausius-Duhem inequality and realized ultimately that S has a volumetric part, S itself has a volumetric part and an isochoric part. So the only thing we have to now do is, what are the forms of this strain energy function? We have already indicated what are the forms of the strain energy function. But we have to go slightly deeper into it. Maybe in the next half a class, we will finish what are the popular strain energy function, okay, and then move back into the finite element formulations. We will stop here and we will continue in the next class with the finite element formulations.